Hello everyone, I'm Chong, a PhD student at University of Miami, and I will give a presentation entitled Effects of the Hunga Tonga-Hunga Eruption on MODIS retrieved SSTs. And I will give the presentation from those five aspects: introduction, data, results, discussion, and some future work. Due to the time limitation, you can find further details from the paper given below. Firstly, introduction. Infrared radiometers on board satellites provide global coverage and frequency SST retrievals, such as the Moderate Resolution Imaging Spectral Radiometer, which is MODIS. The current retrieval algorithms for MODIS, using the channels centered at 11-12 micron, the long-wave infrared atmospheric window, are a modification of the nonlinear SST algorithm with the following form, where Bt11, Bt12 are brightness temperatures at 11-12 micron channels. The surface is a reference SST. Theta is the sensor zenith angle. Mirror represents different size of the MODIS scan mirror. A0 to A6 are monthly algorithm coefficients for different latitude zones. Note that the Bt11-Bt12 difference increases with increasing water vapor column content. However, the aerosol effect on the Bt difference is opposite, and we will show how this aerosol effect is dominant in reducing the MODIS SST accuracy in the following presentation. As mentioned above, the linear SST algorithm mainly accounts for the atmospheric effects of water vapor. However, satellite retrievals are highly affected in aerosol-contaminated regions, for example caused by tropospheric dust from the Saudi Arabian and Sahara deserts. Law et al. In 2019 demonstrated the aerosol effect on MODIS retrieved SST and introduced an improved algorithm for nighttime data in the Saharan dust outflow area. Beyond dust aerosols, dramatic volcanic explosions inject large amounts of aerosol into the stratosphere, such as Mount Pinatubo and El Chichon, the two largest volcanic eruptions in the 20th century. Reynolds et al. In 1989 showed a mean bias of -0.3 K for the AVHRR multi-channel SST from 1982 to 1984 associated with the stratospheric aerosol due to El Chichon. Reynolds in 1993 further studied the impact of Mount Pinatubo aerosols on AVHRR SST, where nighttime data had average negative biases with magnitudes greater than 1K between 20° north and 20° south in August and September 1991, even though using an aerosol-corrected equation. The submarine eruption of volcano Hunga Tonga-Hunga, located at 20.5° south, 175.38° west, on January 15, 2022, was the most explosive eruption since Mount Pinatubo in 1991, with a volcanic explosivity index of 5. Differing from the terrestrial volcanoes mentioned above, Tonga volcano injected an unprecedented mass of H2O into the stratosphere, up to 146 teragram, about 10% of the total stratospheric burden. In contrast, the sulfur dioxide injection was surprisingly low, estimated about 0.4 teragram from several satellite instruments, whereas Mount Pinatubo lofted about 20 teragram as O2 into the stratosphere. However, it was still the greatest perturbation of stratospheric aerosol since the Mount Pinatubo eruption, with 1 to 3 teragram of sulfate aerosol injected. Now let's look at the data used for this study. To assess the accuracy of MODIS retrieved SST, a matchup database has been established by collocating satellite-derived SST, brightness temperatures, in-situ drifting buoy SST, and other ancillary information such as time, location, quality level flag, and viewing geometry. The time window between satellite and in-situ measurements is within 30 minutes and the distance is within 10 km. Here the good quality data with quality level 0, which is the best, and quality level 1, which is degraded, are used. The SST bias, delta SST, is defined as the difference between satellite and buoy SST. For the other datasets, firstly we use the MODIS aerosol optical depths at a wavelength of 550 nanometer, and we also take the self-specific optical depths at 1170 per centimeter, retrieved from the Rosenstiel Appleton laboratory. And the ozone mapping and profiler sealing profiler provides the aerosol to molecular extinction ratio, which is analogous to aerosol mixing ratio, and the integrated stratospheric aerosol optical depths. And the microwave link sounder provides the H2O mixing ratio. And finally, we also use the surface and vertical profiles of meteorological data taken from MERA-2 reanalysis, including temperature, specific humidity, and wind speed. Now let's see some results for this study. Our study region is from 40 degrees south to 0 around the globe. Table 1 shows the MODIS SSTs in 2022 generally have an additional 0.1K negative bias and about 26% reduction in the number of matchups compared with 2021, which occur not only throughout the day but also in both quality level 0 and quality level 1 data. The negative biases are more pronounced in quality level 1 retrievals due to their longer path lengths. Those anomalies are associated with the Tonga eruption. Note that the MODIS-derived SSTs are anticipated to be cooler than in-situ buoy measurements by about 0.17K on average due to the coolskin effect. Figures A and B present the spatial distribution of delta SST in 2021 and 2022. The right star gives the site of eruption. The increased negative bias in the retrieved SST in 2022 are distributed in the whole zonal area, so are the drops of the data volume. In the region centered around the location of volcanic eruption, the red box, the mean delta SST reaches minus 0.53K with a reduction in the number of matchups up to 36%. Figure C further demonstrates the more frequent negative delta SSTs after the eruption, but the shape of the distribution is barely changed. Therefore, such a negative offset of delta SST indicates an undercompensation in the NLSST atmospheric correction algorithm following the eruption. Having included the MODIS AOD retrievals in the matchup database, Figure D shows the delta SST has a significantly negative relationship with AOD. The aerosol effect becomes more pronounced with increasing AOD. Figure E demonstrates the larger fraction of AOD greater than 0.1 in 2022, which strongly verifies the hypothesis of aerosol contamination due to the Tonga eruption. As shown in Figure F, following the eruption, there are more smaller particles with effective radii of 0.2 to 0.6 micron, consistent with the model runs from several papers, which is indicative of increased sulfate aerosol concentrations. On the following day of eruption, January 16th, an increase of spherical particles with low depolarization was detected, suggesting the fast formation of sulfate aerosols. The rapid conversion of SO2 to sulfate aerosols is at least 2 times faster than expected and has been explained as the presence of abundant H2O in the plume injected into the stratosphere, leading to the accelerated oxidation of SO2 to sulfuric acid. Therefore, we consider the enhancement of sulfate droplets as the predominant aerosol effect on the MODIS SST retrievals after eruption. Over the following weeks, the sulfate plume was quickly transported zonally by prevailing easterly winds in the stratosphere, as shown in figures A to E, using the MSSOD data. The extent of the aerosol plume was largely consistent with strongly hydrated layers detected by the MLS. To better review the impact of this advection on MODIS SST, 4 subregions are divided by longitude. Additionally, the matched-up SSTs are selected within the 30 degrees south to 10 degrees south latitude band, and the statistics of delta SST are shown as box plots in Figure F. Some patches of plume were observed again in northern Australia at the end of January, showing a complete circumnavigation in 2 weeks. By mid-February, abnormally negative delta SSTs recurred in regions 1 and 2, and the leading edge of the plume near 5 degrees south caught up with the slowest at 25 degrees south, covering all longitudes. Overall, the evolution of negative MODIS SST anomalies are in good agreement with the footprints of sulfate aerosol plume in the months following the Tonga eruption. With time, the volcanic aerosol plume continued to elongate and disperse over the whole southern hemisphere tropics, and was subsequently transported poleward by the Brewer-Dobson circulation in weeks to months. As shown in Figure A, the stratospheric aerosol plume was transported within the barrier of the tropical pipe from January to May. The poleward transport of the aerosol increased in June when the BDC in the tropics is enhanced during the southern hemisphere winter, with the second core of the extreme SAOD extending beyond 40 degrees south. Figures B and C depict the variation of monthly MODIS SST anomalies in 2 latitude bands, showing significant negative correlations with SAOD anomalies. For 20 degrees south to 0, the aerosol effect on SST reached a maximum in March, whereas it was insignificant initially and more pronounced later at 40 degrees south to 20 degrees south. Note that the correlation coefficient between SST and SAOD anomalies for 40 degrees south to 20 degrees south is only 0.66, much lower than that for 20 degrees south to 0, which is 0.91. This might be explained as the larger sampling errors caused by clouds in MODIS SST at mid-latitudes. Figures D and E provide the temporal evolution of aerosol to molecular extinction ratio field, and the major enhancements of aerosol concentration center on mid-stratosphere with some anomalies extending down to the tropopause. The aerosol layer is descending due to gravitational settling, more pronounced at 40 degrees south to 20 degrees south, separating from the bulk of H2O gradually rising with the diabatic circulation. To quantify the aerosol-induced error in MODIS SST, Artitov atmospheric radiative transfer model was used. The 2021 matchup database was matched with the meteorological fields from the MERA2 reanalysis as model inputs, as the majority of stratospheric aerosols is sulfate droplets. The optical properties of aerosols and clouds predefined corresponding tag is used in the simulations. The climatological aerosol profiles generated by the OPAC model are considered as a background aerosol, while the perturbations due to the Tonga eruption are evaluated by the monthly mean ratio of 2022 and 2021 aerosol molecular extinction ratio, shown as the vertical Gaussian-like distributions in figures F and G. Table 2a displays the results for 2 months, February and August, in both latitude bands. The Artitov simulated MODIS SST anomalies due to Tonga volcanic sulfate aerosols generally have good agreements with those from satellite retrievals. The model overestimations could be due to an exaggerated assessment of the growth rate of aerosol concentration. As in the matchup database, the cloud screening algorithm removes most pixels with high aerosol contamination. Now let's make some discussions based on the results. We have shown the negative biases of MODIS SST caused by the Tonga eruption are closely related to the sulfate aerosol from the volcanic plume, which was mainly concentrated in the mid-stratosphere. Theoretically, aerosol-contaminated infrared satellite SST retrievals are biased low because the aerosol absorbs the infrared emission from surface and then emits at lower temperatures. The current atmospheric correction algorithm mainly compensates for the radiance attenuation by H2O without accounting for the spectral absorptions by stratospheric aerosols connected with volcanic eruptions. Table 2b shows the Artitov simulations for the brightness temperature deficits induced by sulfate aerosol and non-aerosol components in the MODIS 11-12 micron bands after the eruption. Significantly, the BT deficit due to H2O absorption at 12 micron is greater than that at 11 micron, whereas the aerosol-induced attenuation is opposite. Such characteristics lead to undercompensations for the retrieved SST not only from the aerosol-induced BT deficit at 11 micron, but also from a small negative offset of 11-12 micron BT difference by aerosols. The negative offsets of BT difference minus 0.06 K on average are observed in the matchup database in Figure A. Although it has been reported the H2O injection by Tonga eruption into stratosphere is unprecedented in magnitude in satellite era, the total column H2O in the atmosphere tends to be reduced in Figure B, indicating the effect of increased sulfate aerosol on the hydrological cycle as presented in the Mountain Pinatubo case. Therefore, the reduction in brightness temperature difference might also be partially attributed to the total column H2O reduction, which needs to be further investigated. Regardless, the algorithm coefficients should still be robust for the H2O effect compensation since they always account best for the central part of the distribution. So, the future work. Firstly, we can check this effect on SST from the other sensors, and also we can develop an improved algorithm to correct for this aerosol effects. As shown in the figure below, the SST arrow has a correlation with the sulfate aerosol optical depths, but unfortunately this dataset only lasts from January to April in 2022, so it's necessary to find out another strategy. Here are the references. This is my presentation. Thank you for your listening.